Good morning. This is an audio recording for visually impaired students. Today I am going to read a chapter named Non-Aqueous Solvent from Inorganic Chemistry written by Dr. S.P. Zohar. Most of the chemical reactions are carried out in solution, and the behavior of substances also depend upon the nature of the solvent. In the earlier days of development of chemistry, the reaction have been carried out in only one solvent, namely water. It has been facilitated by its ready availability, easy of purification together with its favorable physical and chemical property, such as long liquid range 0 to 100 degrees Celsius, high dielectric constant 78.5, specific heat, heat of volatilization, dipole moment, etc. Water is neutral, odorless, and non toxic. It can therefore be handled safely. The property of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent property of water have hindered the development of non-aqueous solvent. The solvent other than water which are used for carrying out chemical reactions are called non-aqueous solvent. Attempts have been made to find some other solvents which could behave as good solvents like water. Organic chemistry have been using many solvents such as benzene, carbon tetrachloride, acetone, ether for dissolving organic compounds which are soluble in water. Now, there are many other solvents available. For example, liquid ammonia, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly the important feature of non-aqueous solvent such as ammonia and sulfur dioxide, physical property of solvent and their role in chemical reactions. The usefulness of a solvent is determined from its some specific property that may help to carry out the chemical reactions and separate the product more conveniently. Some of the important physical property of solvent are discussed below. First, melting point and boiling point liquid range. The melting and boiling point of a solvent determine the temperature range within which the solvent can exist in a liquid state under atmospheric pressure. Since most of the reaction in solvent system are carried out in liquid phase, the melting point and the boiling point give the temperature range within which the solvent is useful. The melting and boiling point for some common solvent are given in table 1. H2O melting point 0, boiling point 100. Ammonia melting point minus 77.7, boiling point 9 minus 33.4. HF melting point minus 89.3, boiling point 19.5. Sulfur dioxide melting points minus 75.5, boiling point minus 10.2. CH3COH have melting point 16.6, boiling point 118.1. HCONCH3 twice DMF. Melting point minus 61 and boiling point 153. H2SO4 100%, melting point 10.4 and boiling point is 300 with decomposition. It is clear from the above table that water has excellent liquid range 0 to 100 degrees C at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperature, while ammonia and sulfur dioxide can act as solvent only at a low temperature. Second, heat of fusion and heat of vaporization. The value of heat of fusion and heat of vaporization help to know the nature and strength of the force which hold the molecule of the solvent together in the solid or a liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by one molecule of a substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the stronger are the intermolecular binding force in a solid or a liquid respectively. Therefore, the magnitude of molar heat of fusion and molar heat of vaporization give us some insight into the nature and strength of the intermolecular forces, and these also determine the solvent property. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called Toronto constant. Delta H of evaporation by boiling point is equal to Toronto constant. For normal liquid, if molar heat of vaporization are expressed in calorie and boiling point in solvent absolute scale 0 Kelvin, then the Toronto constant has a value 21.5. If enthalpy of vaporization are in joule, Toronto constant is about 94 normal liquids. Such liquid exist as independent molecule without any bond between them. A higher value of Toronto constant indicate associated molecule. For example, common solvent like water, ammonia, hydrogen fluoride have Toronto constant value greater than 21.5 and are therefore associated liquids. The molecule of these liquids are polar. The association of polar molecule is due to their tendency to orientate themselves so that the positively charged end of the molecule come near to each other. The molar heat of fusion and vaporization of some solvents are water molar heat of fusion is 6 and molar heat of vaporization is 40.65. Ammonia have molar heat of fusion 5.65 and molar heat of vaporization 23.56. Sulfur dioxide molar heat of vaporization 7.4 or vaporization is 24. Hydrogen fluoride molar heat of fusion is 4 and molar heat of vaporization is 30.26. The inspection of table 2 show that the value of molar heat of fusion for water and ammonia are almost same. This means the force which hold molecule together in ammonia and water are of the same magnitude. Third is dielectric constant. This property is a measure of the polar nature of the solvent and help to estimate the solubility of polar or non-polar substance in a solvent. According to the Coulombic law, the force of attraction between two charged ions is given by F is equal to Q positive, Q negative divided into sigma R square, where Q positive and Q negative are the charges of the cation and anion respectively. R is the distance between them equal to the radii of the ion. Sigma is a constant which is called a dielectric constant of the solvent. If dielectric constant is large, the force F will be small. As a result, only a small amount of energy will be required to separate the anion and hence it will be easy to dissolve an ionic substance. Thus, in solvent of high dielectric constant, and the ionic substance will dissolve readily. With a decrease in dielectric constant, the solubility of ionic compound will decreases. It is clearly that solvent like HF and H2O are the good solvent for ionic and polar compound because of their high dielectric constant value. On the other hand, solvent like ammonia, sulfur dioxide with small value of dielectric constant show decreased tendency to dissolve ionic compound and especially those containing multi-charged ion. For example, carbonates, sulfates, phosphates are practically insoluble in liquid ammonia or liquid sulfur dioxide. Fourth, dipole moment. The dipole moment is related to the dielectric constant for a solvent. An ionizing solvent has a large dipole moment and also have large dielectric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in a molecule, larger is its dipole moment. Solvent having high dipole moment have great tendency to dissolve the polar or ionic substance. This is because of the fact that greater polarity result in strong bond between the solvent and the solute molecule and large solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecule and help in dissolving the solute. Fifth is the viscosity. Viscosity. It is a measure of the fluidity of the solvent. Solvent like water, ethyl alcohol, and carbon tetrachloride have low viscosity and highly fluid and flow rapidly under ordinary temperature. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbon have high viscosity and flow at much lower rate at ordinary condition. In solvent of low viscosity, the operations such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increase the viscosity of the liquid, increase the difficulty of such operation. Type of solvents. Non-aqueous solvent has been classified in many ways. The following are the important classification based upon the chemical property of the solvent. First is protonic and non-protonic solvent. The solvent from which proton H positive ion can be derived are called protonic or protic solvents. Therefore, protonic solvent contain ionizable hydrogen. Common example are H2O, HF, H2SO4, HCN. Second, non-protonic solvent. The solvent from which proton cannot be ordinarily derived are called non-protonic solvent. These are called aprotic solvents. In the other one, these solvents do not contain ionizable hydrogen atom. Common example are liquid sulfur dioxide, N2O4, C6H6, CHCl3, CCl4. Second, acidic, basic or amphoteric solvent. This classification is based upon the acidic or basic behavior of solvent. The solvent which have strong tendency to donate proton are acidic in nature are called acidic solvent or protogenic solvents. For example, H2SO4, liquid hydrogen fluoride and acetic acid, etc. Solvent which have strong tendency to accept proton and are basic in nature are called basic or protophilic solvent. For example, liquid ammonia, pyridine, hydrazine, ethyl diamine. The solvent which neither have a strong tendency to gain nor a strong tendency to lose proton are called the amphiprotic or amphoteric solvent. In other words, they neither behave as strong acidic or nor basic, but can behave as acidic as well as basic depend upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. Third, ionizing and non-ionizing solvent. The solvent which are capable of undergoing self-ionization or auto-ionization are called ionizing solvent. Some common examples are H2O, NH3, HF, SO2, N2O4, ClF3, BrF3, POCl3. These ionizing as shown below. H2O plus H2O, it will give H3O positive or OH negative. NH3 plus NH3, it will give NH4 positive plus NH2 negative. HF plus HF give H2F positive plus F negative. SO2 plus SO2, it will give SO2 positive plus SO3 2 negative. N2O4, it will give NO positive plus NO3 negative. ClF3 plus ClF3, it will give ClF2 plus ClF4 negative. POCl3 plus POCl3, it will give POCl2 positive plus POCl4 negative. These solvents are generally polar or ionic in nature. On the other hand, the solvent which do not ionize at all are non-ionizing solvent. Some common examples are benzene, carbon tetrachloride, hydrocarbon, etc. These are non-polar or non-ionic in nature. Fourth, coordinating and non-coordinating solvent. The solvent which are capable of coordinating with the metal ion or anion of a solute are called coordinating solvent. For example, ammonia, SO2, dimethyl, sulfur dioxide, acetonitrile, dimethyl, 4-amide, nitromethane, etc. On the other hand, the solvent which are not capable of coordinating with a metal ion are anion of the solute are called non-coordinating solvent. For example, CCl4, saturated hydrocarbon. These are not of much interest to inorganic chemists. Type of reaction in non-aqueous solvent. The following type of the reaction commonly occur in non-aqueous solvent. First, Mathematical or precipitation reaction. The reaction in which precipitation occur on mixing two solutions are called met- metallical or precipitation reaction. These type of reaction can be predicted if the value of solubility product of the compound formed in solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. 2AgNO3 plus BaCl2 in the presence of water, it will give ppt of 2AgCl plus BaNO3 twice. On the other hand, in the liquid ammonia, a precipitate of silver chloride combined with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. 2AgCl plus BaNO3 twice in the presence of liquid ammonia, it will give BaCl2 ppt plus 2AgNO3. Therefore, reversal of chemical reactions take place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water soluble copper sulfate may be precipitated in anhydrous acetic acid. Second is salt formation. The reaction between appropriate acidic and basic substance to form salt are called salt formation reaction. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium uride cannot be prepared by the reaction of urea on sodium hydroxide in water. It is because the strong base available in water, the OH negative, will not take a proton from urea molecule. In the other words, the sodium salt of urea is unstable in water and uride ion will take a proton from water to form hydroxide ion. Na positive, NHCO, NH2 negative plus water, it will give Na positive, OH negative plus urea. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with strong base soda amide. NH2CO NH2 urea react with soda amide in the presence of liquid ammonia. It will give sodium uride plus ammonia. Third is acid base reaction. The acid-base reaction in non-aqueous solvent can be explained on the basis of solvent system concept. As already learned according to solvent system concept, an acid is a substance that by direct dissociation or reaction with the solvent give the cation characteristics of a solvent. Similarly, a base is a substance that give the anion characteristics of the solvent. The acid-base behavior of a substance depend upon acid-base nature of the solvent, the character of the solute, and the solute-solvent interaction. In the case of protonic solvent, cation is the solvated proton and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH4 positive ion act as an acid and NH2 negative ion act as a base. The neutralization reaction is NH4Cl as acid react with base Na NH2. It will in the presence of liquid ammonia give NaCl plus 2 molecule of the ammonia. In non-protonic solvent such as benzene, carbon tetrachloride, Lewis acid, base type of reactions can occur because of non-ionizing of the solvent. The acid-base behavior of a solute in a solvent depend upon the acidity or basicity of the solvent. For example, acetic acid behaves as strong acid in ammonia, weak acid in water. But a base in sulfuric acid. CH3COH plus ammonia, it will give CH3CO negative plus and H4 positive. CH3COH act as a weak acid in water, it will give CH3CO negative plus H3O positive ion. CH3COH act as a weak base with H2SO4, it will give CH3C. Fourth, solvolytic reaction or solvolysis. the reaction in which the solvent molecule react with the solute in such a way that the solvent molecule split up into two parts, one or both of which get attached to the solute molecule or ion are called solvated reaction. Since these reactions occur through self-ionization of the solvent, the concentration of either the cation or the anionic is changed. For example, the solvatic reaction in water, ammonia, and ethanol are given below. Water as solvent, H2O, it will give H3 positive plus OH negative. SO2 Cl2 plus water, it will give SO2 OH twice plus 2H3 positive plus 2Cl negative. F negative plus water, it will give HF plus OH negative. Second is ammonia as a solvent. Ammonia, it will give for NH4 positive plus NH2 negative as an auto ionization. SO2Cl2 plus 4 ammonia, it will give SO2 NH2 twice plus 2 NH4 positive plus 2 Cl negative. H negative plus ammonia, it will give NH2 negative plus water. Third, alcohol as solvent. 2C2H5OH, it will give C2H5O, H2 positive plus OC2H5 negative as an auto ionization. SO2Cl2 plus ethanol, it will give SO2OC2H5 twice plus 2C2H5O H2 positive plus 2Cl negative. CH3 plus C2H5OH, it will give OC2H5 negative plus CH4. It may be noted that in case of solvent like water, ammonia, alcohol, acetic acid, the term hydrolysis, ammonialysis, alcoholysis, and acetolysis are used respectively. Fifth is solvation. The reaction in which the molecule of solvent get attached to the solute species, cation, anion, or molecule are called solvation reaction. The species formed is called solvate. The solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammoniation, alkylation, etc. And the resulting solvates are called hydrate, aminates, alcoholates, etc. For example, copper sulfate with ammonia, it will give aminoate. CuCl2 plus water, it will give hydrate. BSO4 plus H2SO4, it will give solvate of sulfuric acid. Solvation of a cation occurs through ionic ion dipole interaction between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecule donate a pair of electron to the cation. On the other hand, solvation of anion occurs through ionic ion dipole interaction between negative and positive end of the solvent dipole, or through hydrogen bond in case of solvents such as water, ammonia, or hydrogen fluoride. It may be noted that in certain cases it is difficult to distinguish between solvation and solulysis because in many solvatic reactions the first step consists of solvation reaction. However, the term solvation is used for those reactions in which the solvent molecule remain in resulting product. Let us discuss some reaction in two common non-aqueous solvent, liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solvent. It is now used as highly useful solvent and a reaction medium for many type of organic and inorganic synthesis. Its most of the physical property resemble those of water. Comparison of property of liquid ammonia and water. The comparison of property of liquid ammonia and water reveals the following points. First, liquid range. The melting and boiling point of liquid ammonia are lower than those of water. In case ammonia, the liquid range is from -77 to -33 degrees Celsius, and therefore it presents some handling problem. Therefore, some precautions have to be taken while using liquid ammonia as solvent. It is generally handled in cooled vessel, and nowadays a wide range of techniques have been advanced for handling it. Second, hydrogen bonding. Like water, liquid ammonia is an associated solvent through the hydrogen bonding because it contains a strongly electronegative element nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen, and therefore NH bond is weaker than OHO bond. As a result, the freezing point and boiling point of ammonia are less. Since ammonia is less associated with than water, it is better solvent for organic compound. Third is dielectric constant. The dielectric constant for ammonia 22 at minus 33.5 degrees Celsius is lower as compared to water. 78.5 at 25 degrees Celsius, suggesting its lesser tendency to dissolve ionic compound. Liquid ammonia is therefore a poor solvent for ionic substance. Soluble salt include its most ammonium salt, nitrate, thiocyanate, and iodide. Fluoride and main oxazole are generally insoluble. However, ammonia has lower viscosity than water, and this might be expected to promote great ionic mobility and thereby compensate to some extent for the effect of dielectric constant. Fourth, self-ionization. Both ammonia and water show comparable self-ionization as presented below. To ammonia, it will give NH4 positive plus NH2 negative, and to water molecule, it will give hydronium ion plus hydroxyl ion. However, the extent of the auto-ionization of liquid ammonia is less than that of the water. This is clearly from its low specific conductance and lower ionic product. KNH3, it will value 1.9 in multiplied 10 power minus 23 at minus 50 degrees Celsius, and K of water is equal to 10 power minus 14 at 25 degrees Celsius. Therefore, ammonia can conduct electricity to a favorable extent. Ammonia as a better solvent than water. The following property of ammonia may make it a better solvent than water. First, it is a very poor conductor of electricity. Second, the specific heat of ammonia is more than that of water. Third, liquid ammonia is less viscous than water. Most solvent when dissolved in liquid ammonia conduct electric current better than in water. This is not due to ionization power of ammonia, which is about 1 by 3 of water, but due to low viscosity, which greatly increases the mobility of an ion. Fourth, liquid ammonia has high critical temperature and pressure. Fifth, it is less associated than water due to lesser hydrogen bonding, and therefore it is better solvent for organic compound. 7. Sixth, liquid ammonia forms strong reducing metal ammonia solution with alkali metal. Therefore, it is an excellent solvent for many reduction reaction. Reaction in liquid ammonia. As mentioned earlier, ammonia has water-like property as a solvent. It is therefore expected that the reaction which take place in aqueous solution can also occur in ammonia solution. Some of the important chemical reaction occur in liquid ammonia are given below. First, acid-base reaction. The acid-base reaction in liquid ammonia can be easily understood by comparing the reaction in water. 2H2O, it will give H3O positive plus OH negative. According to solvent system concept of acid and base, the substances producing H3O positive ion in water act as acid while those producing OH negative act as a bases. Liquid ammonia ionizes as 2 ammonia, it will give NH4 positive plus NH2 negative. Therefore, the substance producing ammonia ion NH4 positive in liquid ammonia behave as acid, while those producing amide ion NH2 negative behave as base. For example, ammonium salts such as ammonium halides, thiocyanates, nitrates are soluble in liquid ammonia behave as liquid acid. NH4Cl in liquid ammonia give NH4 positive plus Cl negative. Similarly, amide, imides, nitrites behave as base in liquid ammonia. The commonest base in liquid ammonia is potassium amide. In presence of liquid, it will give K positive plus NH2 negative. Lithium amide, sodium amide, and alkaline earth metal amides have a very low solubility, and therefore KNH2 is a commonest base in liquid ammonia. Proteolysis. Certain compound like urea, acetamide, sulfidamide, etc., which are incapable of donating proton to water, can readily donate proton to ammonia in liquid ammonia. Those reactions are called proteolysis reaction, and hence this compound act as acid in liquid ammonia. Acid base neutralization. In aqueous solution, the process of neutralization of strong acid and a strong base involving the combination of H3O positive from acid and OH negative from base to form practically unionized water. For example, neutralization of hydrochloric acid and sodium hydroxide give NaCl plus water, or H3O positive plus OH negative. It will form two molecules of water. In a similar way, the neutralization of an acid and a base in liquid ammonia involve the combination of NH4 positive ion from acid and NH2 negative ion from base. NH4Cl plus KNH2 in it will give KCl plus 2 molecule of ammonia. NH4 positive plus NH2 negative in presence of liquid ammonia, it will give 2 molecule of NH3. There are many examples of amphoteric behavior in liquid ammonia. The compound that dissolve both in acid and base are called amphoteric substances. For example, in liquid ammonia, zinc amide show amphoteric behavior analogous to that of zinc hydroxide in aqueous solution. At a base plus acid, it will give ZnCl2 plus 4 ammonia. NH zinc OH twice plus 2 HCl. In presence of water, it will give ZnCl2 plus 2 molecule of the water. As an acid, Zn NH2 twice plus K NH2 in presence of liquid ammonia, it will give K2 Zn NH2 4. Thus, acid give NH positive ion and base give NH2 negative ion in liquid ammonia. These are termed as ammono acid and amino base. A reaction of ammono acid. Ammono acid is a substance that furnish NH positive ion in liquid ammonia. Ammonium halide, nitrite or thiocyanate are very soluble in liquid ammonia, giving NH4 positive ion, and their concentration solution act as amino acid. We know that acid give hydrogen with metal in aqueous solution. In a similar way, the amino acid solution of amino salt in liquid ammonia react with alkali and other metal to give hydrogen. Na in the presence of NH4Cl, it will give 2 NaCl plus 2 ammonia plus hydrogen. Magnesium plus 2 molecule of NH4Cl, it will give MgCl2 plus 2 molecule of ammonia plus water. A saturated solution of ammonium nitrate in ammonia also dissolve many metal oxides similar to their behavior in aqueous acid. Na2O plus 2 NH4Cl, it will give 2 NaCl plus 2 ammonia plus water. Ca cobalt oxide plus 2 NH4Cl in presence of liquid ammonia, it will give CoCl2 plus 2 molecule of ammonia plus water. Solution of ammonia halide in liquid ammonia may be used as acid in the precipitation of saline and aracine. Mg2Si plus 4 molecule of NH4Br in presence of liquid ammonia, it will give SiH4 plus 2 MgBr2 plus 4 molecule of ammonia. Na3As plus 3 molecule of NH4Br in the presence of liquid ammonia, it will give ASH3 plus 2 NaBr plus 3 ammonia. B. Reaction of amino base. Amino base is a substance which in liquid ammonia solution give an H2 negative ion. The commonest base is potassium amide, which is much more soluble than lithium and sodium amide. Metal salt react with ammonia base to give amides, imides and nitrites which get precipitated in liquid ammonia. AgNO3, it will give KNO3 plus pipette of silver amide. PbI2, it will give the precipitate of PbNH. BiI3, it will give precipitate of bismuth nitrite. HgI2, it will give the precipitate of mercuric nitrite. Second is precipitation reaction. Precipitation reaction involve double decomposition because of the difference in the solubility of various substances in water and the liquid ammonia. A large number of precipitation reactions which are not normally possible in water have been reported to occur in liquid ammonia. For example, silver chloride is precipitated in aqueous solution. KCl plus AgNO3, it will give AgCl plus KNO3. Similarly, a white precipitate of BaCl2 is produced when the solution of silver chloride and barium nitrate in liquid ammonia are brought closer. 2AgCl plus BaNO3 twice, it will give BaCl2 plus 2 molecule of ammonia nitrate. Lithium chloride may be precipitated by the reaction of ammonium chloride and lithium nitrate in liquid ammonia. NH4Cl in the presence of lithium nitride, it will give LiCl plus NH4NO3. Iodide and bromide get precipitated when solution of various nitride and ammonium halide in liquid ammonia are mixed together. Zinc nitride with the NH4I, it will give zinc iodide plus 2 molecule of NH4NO3. Many metal sulfide can be precipitated in liquid ammonia by ammonium sulfide from nitrate solution of the metal. NH4 twice S plus 2 AgNO3, it will give Ag2S plus 2 molecule of NH4NO3. NH4 twice S plus CuNO3 twice, it will give CuS plus 2 molecule of NH4NO3. And no NH4 twice sulfur plus cadmium nitride thrice, it will give CdS plus 2 molecule of NH4NO3. Third is ammonolysis. The solvaceous reaction in liquid ammonia are called ammonolysis or ammonolytical reaction. These are analogies to hydrolysis reaction and involve the attachment of ammonia ion or amide ion to the reactant. For example, hydrolysis of SiCl4, it will give salicylic acid SiOH4. Similarly, ammonolysis of SiCl4, it will give tetraamidocylene plus 4 molecule of NH4 positive plus 4 molecule of Cl negative. SiNH2 4 at 0 degree C, it will give SiNH NH2 twice. At 1200 degree C, it will give Si3N4. It may be noted that in ammonolysis, an atom or ion form a substance is replaced by a nitrogen containing ion or radical. Some ammonolysis reactions C2H5COOCH3 plus ammonia, it will give C2H5CONH2 plus CH3OH. In excess of liquid ammonia, the ammonolysis of TiCl4 occur in steps. TiCl4, it will give TiCl3 and H twice. In presence of liquid ammonia, it will give TiCl2 and H2 twice, and at last it will give TiNH24. When organic halides which undergo slow ammonolysis are ammonolyzed at boiling point of liquid ammonia, mixture of primary, secondary and tertiary amines are obtained. Rx plus 3 molecule of ammonia, it will give primary. Rx plus RNH2 plus ammonia, it will give secondary. Rx plus R2NH plus ammonia, it will give tertiary, where X is chlorine, bromine, iodine and fluorine. Through ammonia molecule is basic and has strong tendency to accept proton and therefore it will act as a base. However, towards very strong base, it acts as a proton donor. Example of this type of reactions are NaH plus ammonia, it will give NaNH2 plus hydrogen. Na2O plus 2 molecule of ammonia, it will give NaNH2 plus H2O. Fourth is complex formation reaction. Many complex formation reactions in liquid ammonia are reported, which are similar to reaction occur in an aqueous system. For example, zinc nitrate react with potassium amide to form insoluble zinc amide, which dissolve in excess of amide due to the formation of complex compound of zinc. This reaction is analogous to the reaction of zinc nitride with sodium hydroxide. It will give insoluble zinc hydroxide in water. Some other complex reaction in liquid ammonia, CuCl2 with liquid ammonia, it will give CuNH34Cl2. AgCl plus liquid ammonia, it will give AgNH3 twice Cl. CrCl3 with the ammonia, it will give CrNH36Cl3. Formation of ammoniates. Just as water form hydrates, ammonia form aminoids with many inorganic salt. In this compound, the ammonia molecule are coordinate to the cation. Some typical ammoniates are BF3 plus ammonia, it will give BF3 dot NH3. MgI with liquid ammonia, it will give MgI2 dot 6 ammonia. SiF4 plus ammonia, it will give SiF4 plus 2 molecule of ammonia. NiI2 plus 6 molecule of ammonia, it will give NiI2 plus 6 molecule of ammonia. Sixth, redox reaction. Liquid ammonia acts as an excellent medium for redox reaction. In liquid ammonia, the oxidizing action of strong oxidizing agent is weaker than in water solution. For example, HNO3 in liquid ammonia does not act as an oxidizing agent. Similarly, KMNO4 in liquid ammonia act as a weak oxidizing agent. On the other hand, reducing agents show increased reactivity. For example, alkali metal act as a very powerful reducing agent in liquid ammonia. For example, sodium metal in liquid ammonia reduce CuI to copper, KMnO4 to K2, MnO4, etc. Seventh, solution in liquid ammonia. The dielectric constant of liquid ammonia is low. Therefore, it is expected to be a poor solvent for ionic substances. Amongst the inorganic compound, all ammonia salt, nitrate, thiazide, and iodide are soluble in liquid ammonia. Oxides, hydroxide, carbonates, phosphates, sulfates, and most of the sulfides are insoluble. Most chloride are insoluble in liquid ammonia, and the solubility among halides increases as fluorine, then chlorine, then bromine, and iodine. Most of the iodides are soluble. Calcium and zinc chloride, which are extremely soluble in water, are quite insoluble in ammonia. Organic compound such as halogen compound, alcohol, ketones, esters, simple ethers, phenols, amines, nitro compound are readily soluble in liquid ammonia. Aromatic hydrocarbons are sparingly soluble. Paraffin and benzene are not soluble. Amongst the element, metal like magnesium, aluminium, zinc, calcium, manganese, etc. are only slightly soluble in liquid ammonia. Alkali metal and alkaline earth metal are highly soluble in liquid ammonia. These form very interesting solution are discussed below. Non-metal like sulfur, phosphorus, iodine are soluble in liquid ammonia. Solution of alkali metal in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metal. The resulting solution are blue and extremely good electrical conductors. The important characteristics of alkali metal solution are they are blue in color and the color is independent of the metal dissolve. When the concentration of metal is increased, the color change to bronze and show metallic appearance. Third, these solutions are conducting and show strong reducing properties. These solutions are paramagnetic and paramagnetic character decrease with increasing concentration. If the reagent are pure and dry, sodium solution in liquid ammonia are stable and can be preserved for several days. When alkali metal are dissolved in liquid ammonia, they ionize to give metal and unbalanced electrons. Sodium it will give Na positive plus electron. Both alkali metal anion and electron become solvated by anion molecule. Na positive it will react with X ammonia molecule, it will give ammoniate cation, plus electron plus Y molecule of ammonia, it will give ammoniate electron. The complete reaction may be written Na it will give Na positive NH3X positive plus electron NH3Y negative. The ammoniate electron are responsible for blue color of the solution. This is due to the absorption of visible light by ammoniate electron. The electrical conductance is also due to the ammoniate cation and ammoniate electron. The conductivity of a metal in pure ammonia is comparable to that of aqueous solution of typical ionic compound. As the concentration of the solution is increased, the ammoniate cation and electron associated resulting in the decrease of conductivity. Very dilute solution of alkali metal in liquid ammonia are metastable and when catalyzed they undergo decomposition. Electron NH3Y negative in the presence of Fe2O3 it will give NH2 negative plus half of hydrogen plus Y minus 1 ammonia. As the concentration of metal increases, blue color changes to bronze and finally the blue color disappear altogether. This is due to fact that impurities such as iron oxide catalyzes the conversion of metal into amide. 2m plus ammonia, it will give 2m NH2 plus water. On evaporating the alkali metal ammonia solution, the alkali metal can be recovered. The strongly reducing character of the solution is due to the presence of readily available electron. The important application of alkali metal solution in organic chemistry is the reduction of many functional group and unsaturated compound. As already studied, the liquid ammonia is a thoroughly studied non-aqueous solvent. Some of its advantages and disadvantages of the solution. Advantage of the liquid ammonia solvent. Decomposition of alkali metal without chemical reaction is one of the greatest advantages by using liquid ammonia as a solvent. The dissolved alkali metal can be recovered from solution by evaporation. Second, the alkali metal solution are strong reducing agent, even stronger than hydrogen. Third, ammonium salt dissolved in liquid ammonia act as amino acid and these find application in preparative chemistry. They can be used for preparing arsenic, etc. Fourth, the tendency of solvences is less in liquid ammonia than in water. Disadvantage of liquid ammonia as a solvent. The liquid range for liquid ammonia is from minus 33.3 to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working with liquid ammonia. Second, liquid ammonia has an offensive odor, therefore, it requires special technique to use it as a solvent and as a reaction medium. Third, liquid ammonia is hygroscopic in nature and hence all the reactions are to be carried out in the sealed tube. Liquid sulfur dioxide. Liquid sulfur dioxide is a non-protonic solvent or aprotic solvent because it does not contain any hydrogen atom. It is also one of the important non-aqueous solvent and has been widely used in industry. Under normal condition of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and easily maintained in a liquid phase. It has a wide liquid range minus 10 degrees C to minus 75.5 and can be used as a solvent. It can be easily purified by passing the gas through sulfuric acid and through P2O5 to remove trace of water. Its dielectric constant is small and therefore is a good solvent for covalent compound. Structure of sulfur dioxide molecule. Electron diffraction studies have shown that sulfur dioxide in gaseous phase has the angular structure as ahead. The valence bond theory predicted that SO2 molecule is a resonance hybrid of the following resonating structure. Autoionization of SO2. Pure SO2 is a poor conductor of electricity. Through it is believed to autoionization S. To SO2, it will give SO2 positive plus SO3 2 negative. The thionyl ion is analogous to the hydronium ion and ammonium ion and sulfide ion corresponding to hydroxyl and amide ion of the aqueous and ammonia system respectively. Reaction in liquid sulfur dioxide. Some important chemical reaction in liquid sulfur dioxide are discussed below. First, acid-base reaction. Liquid SO2 undergo autoionization give SO2 positive plus SO3 2 negative. According to solvent system concept of acid and base, the compound which give thionyl ion in solution of SO2 behave as an acid whereas the compound giving sulfide ion SO3 2 negative in liquid SO2 would act as base. For example, compounds such as SOCl2 in presence of liquid, it will give SO2 positive plus 2 molecule of chlorine. SOBr2, it will give SO2 positive plus 2 molecule of bromine. On the other hand, cesium sulfide increases the concentration of sulfide ion and therefore behave as a base. Typical acid-base or neutralization reaction in liquid SO2 may be given as SOCl2 plus CS2SO3. It will give CSCl plus SO2. SOBr2 plus NCH3 4 into 2SO3. It will give 2 molecule of NCH3 4 bromine with 2 SO2 molecule. Amphoteric behavior is shown by zinc and aluminium ion. For example, AlCl3 react with SO32 negative in liquid sulfur to form insoluble aluminium sulfide, Al2SO3 thrice. However, if the precipitate is treated with excess of sulfide, the precipitate re-dissolve. This reaction is analogous to behavior of AlOH3 thrice in water. If some acid SOCl2 is added to the soluble complex solution, the aluminium sulfide reprecipitate. This reaction is also analogous to reaction in water. Similarly, salt of zinc show amphoteric behavior in liquid SO2. ZnCl2 plus K2SO3, it will give ZnSO3 plus 2KCl. Second, solvatic reaction. Solvatic reaction in liquid sulfur dioxide are not as common as they are other protic solvents such as ammonia. Some reactions are given below. First, ammonium acetate is hydrolyzed in liquid SO2. This reaction is analogous to the reaction of ammonium acetate in water. Certain covalent halides such as PCl5 with the SO2, it will give POCl3 plus SOCl2. Similarly, PBBr5 with sulfur dioxide, it will give POBr3 plus SOBr2. UCl6 plus 2 molecule of SO2, it will give UO2Cl2 plus SOCl2. Many binary halides such as SbCl2, SbCl5, SiCl4, SnCl4, etc. do not undergo solvaces in liquid sulfur dioxide. The formation of solvated, the addition compound with the solvent is also known. Typical example of solvent are NaI.4SO4, etc. Third is precipitation reaction. A large number of precipitation reactions can be carried out in liquid sulfur dioxide due to selective solubility of compound. The precipitation of several insoluble compounds in liquid sulfur dioxide can be carried out by treating them with soluble compound in sulfur dioxide. Some of the reactions are SbCl3 with LiI, it will give SbI3 plus LiCl. BaI2 with Zn2SnS4, it will give Ba CnS twice plus Zni2. Thionyl derivatives can be easily prepared in liquid SO2 by action of thionyl chloride. Fourth, complex formation reaction. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, the solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium or rubidium iodide. This is due to the formation of complex Ki3 or RbI3. Ki plus I2, it will give Ki3. RbI plus I2, it will give RbI3. Similarly, the increase in solubility of cadmium iodide and mercury iodide in liquid sulfur dioxide is attributed to the formation of complex CDI2 with Ki, it will give K2CDI4. HgI2 with 2Ki, it will give K2HgI4. AlCl3 react with SO32 negative ion to form precipitate of Al2SO3 thrice, which redissolve in excess of SO32 negative form the complex molecule. Fifth, organic reaction. A large number of organic reactions have been carried out in sulfur dioxide because organic compounds are soluble in it and it is a relatively inert solvent. Some common examples are: first, sulfonation of aromatic hydrocarbon by sulfur trioxide or chlorosulfuric acid. Second, liquid SO2 has also been used as a solvent for Friedel-Crafts type reaction. In this reaction, AlCl3 is used as a catalyst which is highly soluble in liquid SO2. Third, it is used as a solvent for the addition and substitution of bromine reaction. Sixth, sulfur dioxide for crystallization. These reactions are also called solvation reaction like water, ammonia, salt having sulfur dioxide of crystallization have also been observed. Some examples are NaI.4SO2, KCnNS.SO2. They are formed with a highly soluble salt and are analogous to hydrates. 7. Redox reaction. Through gaseous sulfuric dioxide behave both reducing as well as reducing oxidizing agent. Liquid sulfur dioxide does not show any marked reducing or oxidizing tendency. It simply acts as a medium for certain redox reaction. For example, iodine is liberated from Ki in a presence of SbCl5 in a liquid sulfur dioxide. Some special features of liquid SO2 as a solvent. Liquid sulfur dioxide possesses some special advantage over other solvent as a reaction medium. Some of these are: first, it has low boiling point and this allow its easy evaporation and therefore removal from the reaction mixture. Second, it has low melting point and therefore it allow reaction to be carried out at low temperature. Third, SO2 is an inert solvent. Fourth, it has unusual solvating power for both covalent and electrovalent compound. Fifth, it is a better medium for solvent compound like hydrocarbon and used for purification of some petroleum product. Sixth, it is used as a diluting for a superacid medium HSO3F, SbF5, which help in reducing its viscosity without affecting its acidity. Thanks.